Welcome to Networks Professionals.
How do we actually fix a broken AI? We see these headlines literally all the time, right? Artificial intelligence hallucinating facts, making completely bizarre calculations, or just flat out failing to understand a super simple prompt. And honestly, it's incredibly easy to view AI as this mysterious, unpredictable magic box. But what happens when we stop looking at it as magic and start treating it as a rigorous engineering discipline? Because when an AI model fails, it's not because it ran out of magic dust, it's because there is a structural flaw in exactly how it was built.
Welcome to this explainer on constructing intelligence, demystifying AI reliability. Today, we're going to demystify how reliable AI is actually built. And we're going to do it by looking at the whole process through a lens that makes perfect, practical sense, constructing a building. Let's look past the whole magic illusion and figure out what it really takes to build intelligence that we can actually trust.
Okay, let's dive into this. Our architectural blueprint for today has basically 4 phases. First, pouring the foundation with clean data. Second, drawing up the blueprint through architecture and optimization. Third, installing upgrades using advanced training paradigms. And finally, a thorough inspection via continuous evaluation. Let's get to it.
So let's start right at the ground level with Phase 1, Foundation, putting clean data first.
Look, when you're constructing a skyscraper, pouring your foundation into unstable mud pretty much guarantees the whole building collapses. While in AI, clean data is your concrete. Developers absolutely have to go through rigorous data cleaning steps. We're talking eliminating duplicates, correcting errors, handling missing values, and aggressively removing outliers. If you skip these steps, you're leaving massive cracks in your foundation, and you end up teaching the AI totally wrong patterns before the real structural work even begins.
Now, what's really interesting about this next part is how we choose the materials for that foundation. Engineers use something called feature engineering. You see, you don't just dump every single piece of raw data into the model. Instead, highly sophisticated mathematical filters, things like the Baruta method or principal component analysis, or PCA, are used to sift through the mud. They make sure the model is only using the absolute most impactful variables, stripping away all that useless noise to give the AI the highest quality signal possible.
But hey, sometimes you just don't have enough natural data to build a wide enough foundation. That's where data augmentation comes in. This is a super clever technique that synthetically expands your datasets. Imagine you're training an AI to recognize images. You might augment the data by just rotating those images a bit. Or, if you're working with text, you might add synthetic noise or deliberate edge cases. By artificially expanding that foundation, you prevent the model from overfitting. Basically, you stop it from rigidly over-memorizing a super narrow set of patterns, and you force it to learn the underlying concepts from every possible angle.
Now that our foundation is poured and completely solid, let's look at the blueprint. Phase 2, Architecture and Optimization.
So if the data is our foundation, the model's architecture is the structural framing, and developers are constantly fighting this sort of tug of war between two opposing forces here to keep the frame from bowing or snapping. On one side, you have underfitting. Think of it like a building with way too few support beams. It's overly simple, high bias, and just performs terribly. On the flip side is overfitting, high variance. This is a chaotic, overly complex maze of beams that works perfectly for one highly specific scenario but completely fails out in the real world. Optimization is that incredibly delicate balancing act between the two.
To find that perfect balance, engineers use hyperparameter tuning. And to be clear, this isn't guesswork, it is systematic, exhaustive testing. Developers use really powerful tools like Optuna or Scikit-learn's Grid Search V to test thousands of different configurations. They're hunting for the absolute ideal learning rate, the perfect batch size, and exactly the right network depth. It's honestly just like systematically testing different steel alloys in a simulation to find the perfect structural blueprint before you ever start welding beams together.
But here's the thing, even with the absolute right blueprint, models naturally kind of want to overcomplicate things. So the crucial point is that developers have to use regularization to prevent this. Methods like dropout, L1 lasso, and L2 ridge deliberately act as structural constraints. They actually penalize the AI for excessive complexity. By forcing the model to stay as simple and elegant as possible, regularization helps the AI generalize much better when it's finally exposed to brand new, unseen data in the real world. It basically stops the whole thing from becoming an unreadable, convoluted mess.
Another genuinely brilliant architectural trick is using ensemble methods. We're talking about things like random forests, bagging, or boosting. Instead of putting all your faith into one single massive model to make a prediction, you combine multiple individual models together. Think about it. If one model makes a slight error in its calculation, another model makes up for it. By combining them, you average out the errors, which produces a vastly more robust and structurally sound prediction. It's exactly like having multiple load-bearing walls instead of relying on just one.
Moving right along, let's step into Phase 3, upgrades. We're talking advanced training paradigms.
In modern construction, you use prefabricated materials to save a ton of time, right? Well, in AI, the most powerful prefab upgrade is transfer learning. This involves taking massive, pre-trained foundational models that already exist, like ResNet, which already understands the insanely deep complexities of computer vision. Instead of starting from scratch, from zero, you take that pre-trained model and you fine-tune it strictly on your own domain-specific data. This saves absolutely massive amounts of computational resources while instantly boosting the capabilities of your specific application. It's a real game changer.
In that focus on efficiency, let's move to how this builds into a really fascinating process called knowledge distillation. Step 1. You start with these massive, bulky foundation models. They are incredibly smart, but way too heavy to run efficiently. Step 2. You transfer their capabilities. Step 3. You output a lean, lightning-fast structure that you can actually deploy on something like a smartphone without sacrificing prediction quality. You've effectively distilled all the knowledge of the giant model into a highly efficient, lightweight deployment model.
Okay, so we've built the thing. Now we reach the final, absolutely crucial phase, inspection and continuous evaluation.
This is essentially where the building inspector shows up to prove our structure isn't going to just collapse the second it hits the real world. The very first question an inspector asks is your model actually smart, or did it just get a really lucky dataset? To prove it wasn't just luck, engineers use k-fold cross-validation. It repeatedly slices and dices the data, over and over, forcing the model to prove its accuracy every single time. This guarantees the metrics aren't just the fluke of a lucky dataset split.
And this brilliantly illustrates why relying solely on basic accuracy can hide massive, massive flaws. I mean, a model could technically be 99% accurate just by guessing no to a super rare problem every single time. That is exactly why engineers track advanced metrics like precision, recall, F1 score, and AUC ROC curves. Now, without getting bogged down in all the math here, just know these metrics act as a definitive stress test. They don't just tell you if the model made a mistake, they tell you exactly how and where it fails under pressure, revealing the true reliability of the entire system.
So, we've journeyed from cleaning the raw foundational mud all the way up through advanced architectural tuning and finally to rigorous multi-layered inspections. Building reliable artificial intelligence is definitely not magic. It's an exacting, highly systematic engineering discipline. But as you look at the AI assistants, the recommendation algorithms, and all those automated tools you interact with every single day, it leaves us with one highly provocative question. Have the AI tools you use every day actually pass these rigorous tests? Just keep that in mind the next time a model gives you a totally unexpected answer. Thank you so much for joining me for this explainer, and keep questioning the architecture.
Thanks for watching.